Welcome to the Peacademia course on the basics of semiconductors. This lecture is the part 1 of the MOSFET discussion. Let's start. By the time you finish this lesson, you will learn the field effect transistor categories, MOSFET and BJT differences, and the MOS capacitor. So far, we have had a long journey over the semiconductors in this course. We've seen a PN junction diode, PIN diode, Schottky diode, LED, photodetector, solar cell, BJT, thyristor, triac, and GTO. Quite a long list of devices. In this course, I am going to introduce you one of the most used switching devices used in the power electronics. That is the metal oxide semiconductor field effect transistor or MOSFET. In fact, in the majority of cases, MOSFETs are preferred. And if it was not possible to use MOSFETs, other types of switching devices are employed. In general, field effect transistors are divided into junction field effect transistor or JFET, metal semiconductor field effect transistor or MESFET, and metal oxide semiconductor field effect transistor or MOSFET. Of course, in this lecture, my focus is on the MOSFETs. MOSFETs themselves are divided into enhancement and depletion, and each one of these are divided into P-type and N-type. It is useful to note that in power electronics, mostly enhancement mode MOSFETs are employed, not depletion mode. You will find the reason down the road in this lecture. MOSFET is a three-terminal device and similar to a BJT can be used either in switching or amplifying applications. However, they have differences. I think it is a good idea to compare the MOSFET and BJT in terms of control, polarity, and current flow. This comparison will help us to decide where to use a MOSFET or BJT in a particular application. The MOSFET is a voltage controlled device. However, the BJT is a current controlled device. In fact, the conductivity of the BJT is controlled by the base current. However, that of a MOSFET is controlled by the gate voltage. MOSFET is a unipolar device, although BJT is a bipolar device. BJT is bipolar because both the electrons and holes are responsible for conductivity. However, in MOSFET, either electrons or holes are responsible for conductivity. In general, bipolar devices are capable to handle higher current densities than unipolar devices. In terms of the current flow, in MOSFET, the current is mostly due to diffusion. However, in BJTs, the current flow is mostly due to drifting. Before I explain how a MOSFET works, it is useful to introduce the MOS diode or MOS capacitor. In fact, this device is the main building block of a MOSFET. If you learn how it works, you'll find understanding the MOSFET operation much easier. A MOS diode or capacitor is made of a single P or N-type semiconductor. Let's consider a PMOS capacitor. Note that when I'm talking about the MOS diode, I do not mean it rectifies current. Diode simply means a two-terminal device. On the right side, I connect an ohmic contact to the P semiconductor, and on the left side, first I add an oxide layer, which is an insulator layer, and then an ohmic contact. By looking at the left terminal of this device, it is evident why it is called MOS capacitor. There is a metal layer, oxide layer, and then a semiconductor layer. If you connect the first letter of each one of these words, you'll get MOS. Now let's connect this device to a voltage source. First, I assume the voltage applied to the device is 0, and another assumption to make is that the oxide layer is empty of any static electric charge. So if I plot the voltage across the P semiconductor, what I can see is a flat line resting at 0 volts. The energy band diagram of this MOS capacitor in equilibrium is given here. Since we have a P semiconductor, the Fermi level is sitting close to the top of the valence band EV. In reality, the oxide layer has some positive electric charge. As far as I'm concerned in this course, it is not required to know why the oxide layer has some positive charges. We can just accept the fact and use it in our discussion. Anyway, for those who want to learn more about the oxide layer, electric charge, or trap charge, the references introduced in the beginning of this course can be consulted. All right. So by taking into consideration the positive trap charges in the oxide layer, the voltage plot across the device is bent up a bit close to the oxide semiconductor junction. These trapped positive charges attract some of the minority charge carriers, electrons, to the oxide semiconductor junction, and therefore the conduction and valence bands bend a bit down near the oxide semiconductor junction. Note that the Fermi level remains fixed since no current is passing through the device. This means we are still in the equilibrium position. If we want to get the flat energy bands, what we need to do is to apply some negative voltage to the gate so as the effect of the trap charges in the oxide layer is compensated. What I do next is applying a positive voltage to the gate. This externally positive voltage applied adds up to the electric charges trapped in the oxide layer. By doing this, the intensity of the voltage level near the oxide semiconductor junction increases. By moving away from the junction, the intensity of the electric field reduces, and at the right terminal, it becomes zero. This positive electric field attracts more free electrons to the oxide semiconductor junction. What happens is that these free electrons recombine with the holes sitting near the junction. If the external positive voltage applied is large enough due to the recombination, all the mobile charge carriers, electrons, and holes cancel out each other, and a thin depletion layer forms. Of course, no mobile charge carriers exist in this region. In this case, the energy band diagrams near the oxide semiconductor junction bend more. Let's increase the voltage of the external voltage source. By doing so, more free electrons are attracted to the depletion region, and since there is no hole to recombine with, the number of electrons in a region close to the oxide semiconductor junction increases. Now, we are facing with a region that its majority charge carriers are electrons but not holes. This means that an inversion has happened. The P semiconductor is inverted into an N semiconductor near the oxide semiconductor junction. This region is called the inversion layer. By looking at the energy band diagram, we notice that EC and EV are further bent down. Remember that in equilibrium, the Fermi level does not bend. So what can we see in the energy band diagram is that the Fermi level near the oxide semiconductor junction is now very close to EC and far away from EV. This is an indication of the inversion. Now you may say, what if I apply a negative voltage to this MOS capacitor? What will happen? Well, this is a really good question, and it is worth it to take some time and talk about it. To start, assume the oxide layer does not have any trapped charges and the voltage applied to the device is zero. So in the energy band diagram, we have flat bands. Now, I apply a negative voltage, so the voltage diagram turns into something like this. What it does is repelling the electrons near the oxide semiconductor junction, and therefore more holes are exposed in this region. In other words, we have more accumulation of majority charge carriers near the oxide semiconductor junction. This region is called the accumulation region. After all these discussions, it is time to ask, why do we call such a device a MOS capacitor? Very good question. Remember that in the structure of the MOS capacitor, we have an oxide layer which is insulated and sandwiched between a conductor and semiconductor. On each side of the oxide layer, we have different amount of charge carriers, and therefore it is a capacitor. Depending on the voltage applied to the device, the capacitance of this device changes. This diagram demonstrates the capacitance versus voltage applied. As you can see, for negative voltages, the capacitance equals C oxide. C oxide equals epsilon oxide times the oxide layer area divided by the oxide layer thickness. By increasing the voltage positively, the capacitance reduces until we get to the threshold voltage, VT. After that, the capacitance increases again and it saturates at C oxide. We need to investigate on why the capacitance reduces when the voltage is increasing from 0 to VT, the threshold voltage. From what I discussed earlier in this lecture, we already know that by applying a positive voltage, a depletion region can form. The larger the positive voltage, the deeper becomes the depletion region. Since in the depletion region there is no mobile charge carriers, it behaves as an insulator layer. So it is clear that under this case, the overall insulation layer gets thicker, and that reduces the capacitance. This capacitance reduction continues until the threshold voltage VT. Above VT, the capacitance increases, but why? This is because a gate voltage larger than the threshold voltage attracts more electrons to the region near the oxide semiconductor region. And since there is no more hole available for recombination, the concentration of electrons increases, and therefore the thickness of the depletion region reduces. This is equivalent to increasing the capacitance. In this lecture, I discussed the field effect transistor categories, MOSFET and BJT differences, and the MOS capacitor. The next lecture is a continuum of this lecture, and you are going to learn more about the MOSFETs. Thanks for joining this lecture of Peacademia.